questions, you should be.
Oh,
yeah, great.
thanks, Mike.
Apparently
Okay.
I can do it.
Okay,
Okay.
thanks.
I've
Thanks.
never actually tried it before, so I guess I can just upload it to YouTube or something.
Sure. Sure, that would be
Yeah.
nice. Thank you.
So, if you have any questions, just like the last time, I think you should ask them as we go, rather than in the end, because if you don't understand something, you may end up uh, uh, being unable to understand most or everything of what follows, right? So I thought we do need to review the basics first. So what's a category? We have objects and morphisms, and in a way that you can connect the morphism. So we draw morphisms as arrows in diagrams, and each morphism has a beginning and an end. Yeah, and every object has an identity morphism associated with it. So here you can see identity for Y, and everything else also has an identity for it. And you can compose morphisms. So you have H and G. You can have H dot G. This is the notation for composition. And same with F and G. And there are two properties of composition, namely that it is associative, that is, it doesn't matter whether you compose these two first and then add this one, or if you compose these two first, get this, and then add this one, should that must result in the same morphism. And the other property is that identities are neutral elements of composition, both left and right neutral elements. So if you compose an identity to the right, that doesn't change the morphism. And if you compose to to the left, that gives you the same morphism. And same to the right. If you compose to the right, that gives you the same morphism. So yeah, that's categories. Now there are important examples of or special cases of categories that we will be using. So if you have a category C, you can define an opposite category. So C with the notation with the superscript OP, and the objects of the opposite category are the same, and you reverse all of the morphisms. And by the way, the order of morphisms in composition also reverses. So F and G are swapped around here. So another important special case is the product category. So if you have two categories, they have objects and morphisms, right? And now the objects of the product category are the pairs of objects from the first and from the second category. That is, every pair of objects where the first object is from C and the second object is from D is a valid object in the C cross D category. Now same goes for morphisms. So if you have a morphism in C between C1 and C2 and a morphism G in D from D1 to D2, you can form a morphism in the product category, which is a pair of morphisms F and G. I chose to emphasize this. I chose to draw this with double arrows, but the thing is, those are just the morphisms from the category definition point of view. That's it. You need identities and compositions for category too, right? So they are defined component-wise. So identity is going to be a pair of identities, and to obtain composition, you construct compositions in the original categories, and their pair is the composition in the product category. Yeah, I need to mention that there's a term for a set of morphisms given two objects. The important notion is a set of morphisms between those objects, and it is called a home set. So, any questions so far?
Jonathan, do you have any questions?
No, I don't. Or yeah, like I know the basics.
Okay.
So
All
I've
right.
seen.
Is this all familiar to you?
I've seen them before.
Okay. Cool.
Great. So functors, mappings of categories. We have two categories, C and D, and a functor F consists of two functions. The first function maps objects, and there's a more interesting function that maps not really a function, because like there's more structure than just sets, right? But this mapping maps morphisms, and in a way that respects some structure, right? So it maps identities to identities. So FID should be ID on FA, and f of g.f should be fg.ff. Okay, now there are important special kinds of functors that we will be using. If the domain and codomain of a functor are the same, it's called an endo functor. If the domain is an opposite category, it's called a contravariant functor. Remember the opposite category from the categories definition. So everything that's not a contravariant functor or a bifunctor is sometimes just called a covariant functor. So if you have a product category as your domain, that kind of functor is called a bifunctor. And it's important that there are no opposite categories in this product. This is called a bifunctor. So it's gonna map pairs of objects to objects and pairs of morphisms to morphisms.
I have a question.
Okay.
Is E also a product category in that case?
Not necessarily. It's just a category. Yeah, can be anything.
Okay.
So the important thing is that the domain is the product category. That's when f is a bifunctor.
I see. Okay.
It doesn't really matter what codomain is. And yeah, we'll see if you pick an object either from C or from D, you get new functors, which are regular covariant functors rather than bifunctors, because they're not functors from a product category anymore, right? And if in your domain that is a product category, one of the categories is an opposite category, and the codomain category is set, that, in other words, it's a set valued functor. That kind of functor is called a profunctor. Profunctors that we'll see. Remember sets of morphisms. So given two objects, there's always a set of morphisms between those objects. So there's this profunctor called home profunctor. Takes a pair of objects and gives you an object in the category set, which should be a set, right? So that is its action on objects, and we also need to understand its action on morphisms. So a morphism in here is a pair of morphisms, right? It needs to send this morphism to a morphism in set. Yeah, I should have introduced the set category, right? The category of sets. So in set, the objects are sets or data types, if in the context of programming, and morphisms are functions. So a morphism from this category needs to be sent to a morphism in this category, which is a function. This is how this function it defines. So one parameter g, and you post-compose h to g and pre-compose f to g, and that is an element of a new home set. So if you generalize this and add covariant functors here, you get these images of objects and these images of morphisms. You see, here we, before using the composition, we mapped the morphisms with functors g and f. Yeah, I need to mention that if we have a profunctor or a contravariant functor or something involved an opposite category in the domain, we do not explicitly construct a morphism in C-op. We just describe a mapping of morphisms directly. So in the opposite order. So the domain and codomain go in the opposite order, right?
So I have a question on your notation here. So,
okay.
So in the line that says hom equals what our hom colon, yet that arrow
I am just yeah, using, so it's kind of parameters. I could do like lambda
Oh yeah,
a
that's fine.
b.
Yeah.
Uh,
So that arrow there is a functor, right?
yeah, this guy is a functor, and this is my like pseudocode of sorts
But
for
that arrow
the
is
action on morphisms. So
that
this is
arrow,
like lambda g.
right? So my question is that second arrow, the G arrow, is not a functor, right? That's some other type of arrow,
Mm.
or is it?
That is just to write down the function.
But what's the function in this case? G is the function,
The
right?
function takes g as an input and
Is it a
produces
member of?
this morphism as an output.
Yeah. So what is G's type? You know, or I mean, what is it a member of?
G's type. So let's say you have A and B. G's type is an element of the set on A B,
Okay.
and you have a set. You have A prime and B prime, and you also have a set called A prime B prime, and this guy is from A prime B prime.
Yeah. So this would be a lot clearer if you wrote that down, because I'm still.
Yeah, I am omitting a bunch of things here because just the preliminary introduction would be too long if I did all of that.
Yeah, I got you. I don't. One thing that might be nice too is what is the hom minus equals notation?
Yeah. So I'm doing this to avoid introducing variable parameters like this. Think of it as it takes A and B to A and B. So if you're familiar with Scala, they have a similar kind of notation for lambdas. So they can do like this is the same as this in Scala.
Mm-hmm.
And this is common in category theory texts,
Okay, gotcha.
including Milewski's.
Okay, gotcha.
Right, so natural transformations. So we have two categories, and we have two functors going from one category to the other. So both have the same sort of signature, and that is what you need to be able to have a natural transformation. Now, a natural transformation is a family of morphisms in D. So if you pick an object X, you're gonna have two objects, Fx and Gx, right? And a natural transformation is gonna pick a morphism from Fx to Gx, and it is called the component of alpha at X. So alpha is the name of the natural transformation here. So I am doing this to the object A. I have the component of alpha at A, and same to B, the component of alpha at B. So a natural transformation is a family of morphisms like this. In this, you have a morphism like this for any object in C. Now, the condition on these morphisms for them to be called natural transformation is that this square needs to commute. So this is the condition. So any questions about the definition?
Other than like, why is it interesting? Natural transformation.
Because you define adjunctions with it in like a lot of. Okay, so either like this. If you want to learn a lot of category theory easily, you need to get good at natural transformations. Yeah, that's my line here. Yeah, and in let's say in set or in Haskell, in like programming, polymorphic functions are natural transformations. Like save safe and cons, or like list to maybe, is a natural transformation. It's polymorphic, right? And it involves two functors. And also, let's say length is a natural transformation. The functor at the codomain is a bit weird, but it's a natural transformation anyway. So you can have a composition of natural transformations, which is given by.
I have a question then. So
Okay.
if length is a natural transformation, could I have one that's like sine or something? You know, it goes.
What?
It's like a really weird. Two
Which
functions.
one?
Just any function from some type of value to some other type of value, right? Like if int is a strange functor, then int on both sides is the strange functor on both sides, right? For all a, int goes to int or something.
So what you have, the reason it's a natural transformation is because of this.
Okay.
It's const int a. Yeah, so this is a functor, and this is a functor too.
But couldn't I have constant on both sides, right? As the domain.
Yeah,
domain.
and so if you have a so-called phantom variable, right? With respect to that phantom variable, you can say the thing is a natural transformation. Although I don't know if the compiler will let you have a type variable that is not used.
Yeah.
Okay, so you can have composition by composing the component morphisms component-wise, right? And you can also have identities, so also component-wise identity. And that kind of composition is called vertical composition. And that is important because there is another kind of composition. So this is a diagram in the category of all categories. Yeah, these should be arrows pointing to the right, by the way. So objects are categories, and morphisms are functors. So f and f prime go from C to D, and G and G prime go from D to E. And when you have, so you can have composite functors, right? You can have G dot F, yeah, you can have G prime dot F prime, right? You can have G prime dot F and such. Yeah, and if you have functor compositions like this, and you want to transform between them, and let's say you have a transformation for each of the component of the composition in independently, right? And you can construct a natural transformation which uses these to transform the composite functor. This is called horizontal composition of natural transformation, and it is written as, so at least in the Milewski's book, it's written with this circle, just a blank circle as opposed to dot, right? And by the way, if you see functor composition, you might see dot omitted. So just GF, right, as opposed to G.F. And the component-wise form can be given by one of these two expressions, and they are equal because it's a special case of the naturality square. By the way, this condition is called the naturality square of a natural transformation. And there are important special cases if one of alpha or beta is an identity. Yeah. So the identity natural transformations. If you see this notation, that is the name of a functor in a place where there should be a natural transformation, just know this is the identity natural transformation on that functor. So let's say alpha is the identity, and it is on the right of the horizontal composition. So f ends up in here, and we have a component of beta at fx. And if the identity natural transformation is on the left, we end up with a component at x mapped by g as a morphism with a morphism mapping function. So this is important. So any questions so far?
Yeah. So when it's an identity natural transformation, like if alpha was identity, then f would equal f prime, right?
Right. Yeah.
All right.
That's implied here.
Yeah.
Okay. Great. So let's briefly revisit monads and comonads. They are involved in adjunctions too. First, you need to have an endo functor, and note that I am not using the return bind definition here. Instead, I am using the return join definition. So you know control.monad.join. This is what mu, the natural transformation mu, stands for. In Haskell, it's join. So both of these are natural transformations. This one in Haskell is called return, and this one is called join. And there are laws that these have to be subject to, namely, by the way, this is called, I think, unit, and this is called multiplication. So by analogy with monoids or something. So the idea here is that unit is sort of the left and right identity with respect to the multiplication, and this one is the associativity, which means it doesn't matter if you start joining the monadic layers from the left or from the right. So a comonad is a dual construct. This is called co-unit, also natural transformation. In Haskell, it's called extract, and this is called duplicate. So you see the arrow is sort of reversed here. I think that's co-multiplication, or yeah, not quite sure. But there are also laws that are pretty much the duals of these laws. Yeah, I don't have the diagram here, but this is like the triangle that you see in monad explanations, and this is the square, right? That goes from m cubed to m squared to m, right? Okay, now adjunctions. Finally, we made it. So first, we have two categories, C and D, and the functor L goes from D to C, and the functor R goes from C to D. Now these are called adjoint functors, or they form an adjunction if there's a natural isomorphism between these home functors, which means first, if you pick any D and any C, these two home sets should be isomorphic. That is, a choice of F in LD to C uniquely determines the morphism G in the set of D to RC, and that works the other way around too. Now F and G are called the left and right adjunct, respectively, or the left and right transpose. Yeah, I've seen that too. So phi is the mapping to the right, and C is the mapping to the left. Now it's not just those aren't just functions; those are components of the natural isomorphism. What this means, in particular, for the home functors, is that if I had, let's say, a morphism called X going to D, and a morphism Z going out of C, so X is going to be mapped by L to Lx, right? And this is going to be mapped to Rz. It should not matter if I apply the isomorphism and then compose the morphism, or if I compose the morphism first and then apply the isomorphism. That is what the naturality requirement results into. Okay, there's another definition for adjunctions. So still the same functors, and they are adjoint. They form an adjunction if there is a pair of natural transformations. So eta goes from identity to RL. Here we see a component of the unit at D, and epsilon, called co-unit, goes from LR to identity, and it's called co-unit. They have to be subject to the so-called triangle identities. I don't have the diagrams for them, but those are the equations. Yeah, and this is where the vertical and the horizontal compositions come in. So my intuition about this is that if you have a unit and you apply a co-unit immediately after it, co-unit should cancel out in some sense the unit, and like if you do it in any of the possible ways, like you can do it like this, and you can also do it like this. You cannot just vertically compose them directly, right? Because they go between different pairs of functors. Yeah, so these are two definitions of adjunctions. So any questions so far? Okay, no questions. So these definitions are equivalent, and this is how you express the home set isomorphism in terms of the unit and co-unit. So phi is given by taking an f, mapping it with R, and post-composing it to the component of unit at D. And it works symmetrically for the other directions. So psi for G is defined as mapping it with L and precomposing it to the component of the co-unit at C. Now, we can also express unit and co-unit in terms of.
So I have a question.
Oh, okay.
So why do you even need these units and co-units? Like, shouldn't the LG already be a morphism from D to? Oh, maybe not. Oh, right. Right. Okay. I see the difference. Right. I understand. I think. Oh no, I don't understand.
Yeah, well, they are part of the adjunction. So this is the definition. Like we need them to define an adjunction.
So just go back. I mean, if we're just thinking about L as a functor from D to C, right?
Right. They are functors.
Then if I do L of G, shouldn't that be a morphism from?
L of G is this guy, and we need this guy.
Okay. Okay. So
you see, and the ends don't match.
Right. Oh, okay. Because L of C is not C in the. Right. I guess.
Right. There is no L of C. Right. Because L goes from D to C.
Wow. There has to be an
and
L since it's a functor, right? Functor has to take every.
C doesn't live in D. C lives in capital C. So you cannot have L of C. You can have L of RC.
Oh, right. See? Yep, that makes sense now. Yep. Okay.
And this is the most important diagram in this talk. Like, if you want to get good with adjunctions, yeah, I don't know, memorize it or something. Because a lot of future concepts are defined using it.
So I guess, will we have some examples?
Sure, yeah, the examples are coming.
Awesome.
But let's study the pure adjunctions for just a bit. So we also want to express a unit and co-unit in terms of the home set isomorphism. What we do here is set C from this picture, set C to LD, and set F to identity on LD. You see that? And now apply phi to it. And namely, so you see, phi is a natural isomorphism, that is an invertible natural transformation. And a natural transformation, remember, is a family of morphisms. So it has to be indexed by an object, and it is a natural transformation between pro-functors. So the domain category is a product category, so we need a pair of objects. So we take the component of phi at D and LD and apply it to the identity morphism on LD, and that gives us the component of unit. And that's the reason I I showed 2 to 1, the definition 2 to definition 1 first, because now you can see that this becomes ID, and this whole thing is equal to the component of the unit. And we find the components of, sorry, need to mention this. You can see one of the triangular identities popping up here. So L, circle eta, and this is epsilon circle L. Should be the identity on L, and this is the one of the triangle identities in the component form. And we can do the same in the other direction. So set D to RC, take the component of C at RC and C, and apply it to ID. This is an isomorphism, and it should give us a morphism, which happens to be the component of the co-unit at C. So that is how the two definitions are equivalent. There's a third definition which I haven't included here, but the idea of it is that adjunctions are equivalent to universal properties. You'll see that in a moment. So need to mention that adjunctions give rise to monads and comonads. So unit of the adjunction is the unit of the monad, and multiplication is defined using the co-unit. For the co-monad, the co-unit is the co-monad co-unit, and the duplicate or co-multiplication is defined using the unit. Okay, examples. So we have we take a category C and we construct a product category, C cross C, a product of C with itself. Now we consider the functor delta, which is called a diagonal functor. And what it does for objects is for an object D, it results into a pair of identical objects D and D. And for morphisms, for morphism G, it results in a pair of identical morphisms G and G. And I need to mention, to avoid future confusion, that there are many functors, different functors, but they might all be called diagonal, and this is one of them. Now, I claim that the product functor or bifunctor is defined as the right adjoint to the diagonal functor. So, any questions or discussions at this point? So, if you are familiar with Milewski's category theory for programmers, or a traditional definition of a product object from somewhere else, you know that a product needs to have two projections, and there has to be some sort of a ranking, and that ranking forms some sort of a chain, right, or a DAG or whatever, and the object that we use as the product is at the end of that chain, right? So A cross B with two projections, such that for any other candidate with its two projections F1 and F2, there is a unique morphism G that factorizes those projections. So it expresses the projections of the other candidate in terms of the projections of the actual product. So yeah, this is how the product functor is defined. So you see, product is a functor from C cross C to C. That is, it's a bifunctor. Do you hear me, by the way? Okay.
Yep.
I'm sometimes thinking I went offline or something.
No. Just
We're mesmerized.
we're mesmerized, exactly.
You know what? Let's take a break and take a look at this. Yeah. So product, right? Two projections, and if you take any other candidate and its two projections, there's a unique morphism that expresses these two in terms of the actual best, or the actual projections of the best product.
I am with you. I'm with you.
And by the way, so I remember somebody said this is really nice and easy, and this is complicated, right? And the reason for that is Milewski actually cheated a bit here. You see, these are actually two diagrams. So this is one diagram, and this is the second diagram. And they just happen to have a common pair of objects and a common morphism. That's why he was able to draw them as if it was a single diagram, but it is actually not. And that is why you need the product category. Yeah, and since these guys are identical between the diagrams, here you need to map them with a diagonal functor. That's why it is there.
So the diagonal functor is the gluing together of the two diagrams in the book. Is that what you're saying?
Right. It lets you work with two diagrams in a single category, so that you can use the framework of adjunctions.
Mm-hmm. I mean, honestly, that kind of makes me appreciate the book a little bit more. That's a nice hand wave. That's a very effective and good hand wave.
Like using a single diagram, right?
Yes. That's because even in the beginning, there's like the disclaimer that we're going to hand wave some things here, right? So that's cool. But this is also cool. I like both. This is a very nice, I don't know, it's a nice addendum, like a nice extension from there.
Yeah, it makes more sense once you know Milewski, right?
Yeah. Very cool.
So you have. By the way, do you see what projections are? So projections are the call unit,
Hmm.
and there there is so the unit is an actual Haskell function. I think it's called data.extra.due. Let's look it up. And yeah, so product is a bifunctor. So you should be able, so if CS set or Hask, right? You should be able to get this morphism by using map, right? Okay, so in set, this ends up being a Cartesian product. Okay, I need to mention this, and in Haskell, those are pairs or tuples with two fields, right? And they have a bifunctor instance that has bimap, which lets you do this. And I think in data.extra there should be C for this, or there's definitely a function like this in control.arrow. It's called fanout, or yeah, it's some weird operator, but it's referred to as fanout,
Yes. Yes.
like this or something.
I.
Right, yeah,
That's it,
this
yeah.
one. That should be in extra. Right. Yeah, that's
In
the
reload.
unit. And do we actually have the isomorphism here? The home set isomorphism. Because there's a lot in this library. No, we don't. But yeah, they're easy to construct. Once you have unit and call unit, everything else is easy to construct. And if you have the home set isomorphism, everything is easy to construct too. So if you take a look at the categories and compare it again with this diagram. So see, we need to establish an object with a structure, right? Or like a family of objects with structure. And there, we need to define a ranking between them. Now, the structure is established in the category on the left. So we have projections, and these are projections of the other candidate, right? So this is for the structure, and this is for the ranking. So we see two candidates, D and A cross B, and we see that A cross B is better than D. So you remember this discussion, better or more universal, right? Because it has a morphism going from it to A cross B. This is what you construct in the category on the right. Yeah, this, by the way, applies to right adjoints. So it's going to be swapped for left adjoints. Okay, so that's it for product. And I need to mention that if you rotate this diagram 180 degrees and reverse all of the arrows, the left and the right adjoint swap places, right? So left and right adjoint are duals. And this is what we're gonna see in the code product. So the delta, the diagonal functor is still the same, maps objects and morphisms to pairs of identical objects and morphisms. And now there is also a left adjoint to it, which is the categorical co-product. Oh yeah, one thing that I also need to mention. A category that has the product by functor defined in it is called a Cartesian category.
For no reason, I'm sure.
Well, it's all of this is meant as a generalization of set, right? Like a lot of category theory. So if
Sure.
it's set, this is the Cartesian product of A and B. And the idea is you want to be able to describe those categories that you can have something parallel to the set theoretic notion of Cartesian product, right? So this doesn't necessarily have to be set, but we are introducing a Cartesian product-like object into it. That's the idea, and yeah, I guess that is why they're called Cartesian categories. Yeah, so remember they say that co-product is dual to product, and yeah, that's why it's the left adjoint. So you're searching among objects of C that have that each have a pair of morphisms like this, right? G1 and G2, or I1 and I2. And again,
Thank you. Sorry. All right, we're back.
So if you remember the traditional definition, we are looking for an object in C with two injections, and two morphisms of C means a morphism in C cross C, right? And among all such objects, we need to select the best object according to some ranking, namely that those other projections can be factorized through a unique morphism F. So remember, we have in adjunctions, we have a home set isomorphism. So that isomorphism, namely the C, is going to map G1, G2 pair to F. Yeah. So yeah, take the time and compare that to the compare the traditional definition to the adjunctions definition. Yeah, and I forgot to tell, I1 and I2 are called injections. Yeah, it says projections here. That should be injections. So I1 and I2 are the actual injections. G1 and G2 are the other candidate injections. And again, here now in the category on the right, we have the structure, and in the category on the left, now we have the ranking. And A plus B is the best object because there is a morphism that goes from it to every other object with the structure. And there, so not the projection. The injections are the unit of the adjunction, and there is a Haskell function. So if you take C to be set, I need to tell this. If you take C to be set, this the co-product is called the sum type or disjoint union. So essentially, either or any type with two constructors and one field in each of them, right? And so in Haskell, you do have a function from either C and C to C. It's called, I think, from either. Also from data.extra. Right. Yeah, that's the signature. And do we have anything that transforms morphemes here? Well, I think, no, that's just left and right. Okay, we just have the co-unit here. Yeah, and I1 is the left constructor, and I2 is the right constructor. And by the way, C here, the function that maps G1 and G2 to F is called either in Haskell, so lowercase either. Right, this one. So if you don't like case expressions, right, you can use this, right? It's a so a case expression is already in there, or a pattern matching or whatever, and you don't have to match yourself, right? You just supply the function G1 and G2. So this is the C of the co-product to delta adjunction. Okay, so exponentials. Now we need the same category, both on the left and on the right. And we also need this category to be Cartesian first, because we are about to use the product. And here we are taking an object S, and by fixing it and partially applying the product by functor to it, we are getting an endo functor. So does it make sense how this functor is formed? So a functor of pairing with S, that's what I call it.
With the same notation from before that I asked about.
Yeah. Yeah, I think it would get really clunky if I like introduced A to A cross S, right?
Gotcha. Yeah.
This is conventional. This is all over category theory textbooks.
Gotcha. Okay.
So the idea here is that in a category C, we want to define a function type like object with a notion of function application. So again, there are in the functor that gives you that object, so a functor of exponentiation to S is defined to be the right adjoint to the right adjoint to the functor of pairing with S. And yeah, I'm not including the traditional definition here, but since it's the right adjoint, the idea is roughly the same as with the product. So there are candidate objects. So we are attempting to use D and s and c to the s as exponentials, and we want them to have a morphism that corresponds to application. So if you pair d with s, there should be a way to apply s to d, right? But first you need to pair with s. That's the reason the category has to be Cartesian first. And c to the s is defined to be the best such object. That is the object that has a morphism g from any other candidate object, such that g when acted on by this pairing with the s functor factorizes f. So the co-unit here is called apply. Yeah, if you look at, we need to look at the traditional definition, I think. So Milewski calls it eval, and some also call it apply. Yeah, and I need to explain how the functor of pairing with s acts on morphisms, right? Because it's clear enough on objects, right? It just builds a product object with s, and for morphisms, what it does is it takes a pair of g and the identity of s, and that pair is mapped using the regular product by functor. Yeah, so from this diagram, we see that to go from f to, so if c is set or Haskell, now to go from f to g, you use carry, so phi is carry, the other direction c is uncarry. This guy is apply, so it is function application, so either uncarry application or uncarry ID, right? As we saw in the equivalence of adjunction definitions, you can apply phi to ID and get the c to ID and get the co-unit, the component of the co-unit, right? Now I said that every adjunction it uses a monad and a co-monad, so RL is supposed to be a monad, and indeed we see that this guy is the state monad, right? And if we take S to be the real world, this is the IO monad. Now there's also a co-monad here. LR is supposed to be a co-monad. So this guy, a pair of function and S, is called the store co-monad. Yeah, and epsilon is its extract. So the intuition for the store co-monad is that it's like a table indexed by S's, right? With an entry highlighted in it.
Yep. This is I think I had a breakthrough seeing this diagram. So I kind of feel like I understand everything you're talking about now.
Wow. And you know what? I think it also helps that all of this is the same diagram.
Yep. So I think one thing that would be helpful that I had to kind of do on myself is to show like which objects are being functorized by the XS, right? Like
So whatever you see, like which are acted by the functor, right?
yeah, so like if you left off the blue stuff to start, right, and just
Yeah. So
and should
I'm color coding everything that relates to the same morphism. Yeah. So morphisms are central here. So
yes,
that's why.
Yeah.
This is everything related to F, and this is everything related to G.
Right.
So
I think if you had a separate diagram to start that just had like leave off the F, leave off the blue stuff to start, and say, okay, here's everything like when you do the pair with S. Oh, and you get this transformation.
Right. Like
show the other direction. Oh, this is everything if you do.
Like this guy, right?
Yeah. Instead of here, I had to like figure that out myself. That there's two things going on, but they just happen to match up, and that's where the adjunction comes from, right? Which is cool.
Yeah. So I am not defining the action of the exponential on morphisms. So in a category theory book, you can actually learn like if you don't know what functor that actually is, all you know is like it's a right adjoint, right? There is a way to construct its action on morphisms, which I haven't figured out yet.
Really?
Yeah.
That's very cool.
Like this is like I know how to do this for set, right? How to construct this guy for set, for example, right? But I don't know, like in general case, right?
Mm-hmm. Cool. I got to tell you, this is a lot easier after getting warmed up like a week or two ago. Thank you.
Yeah, great.
Just for everybody that's watching at home, we did a little bit of a cheating prep session last week to prepare. That was good.
Okay, so the category C that has exponentials defined in it, it's called a Cartesian closed category. So remember it first. Do you notice that there are no closed categories, only Cartesian closed categories? That's why to have a concept of application, you need to have a concept of pairing with an argument first. That's why it's always Cartesian closed.
And that's in the same usage as like a closed. That's like monoid closure, right? Like algebraic closure. Is that? I'm wondering if that's the same use of closed.
Is like if okay, let's start with C being set. So this is this object is meant to be isomorphic to an object in set, right? So exponentials in set are meant to be isomorphic to home sets. So sometimes it's called the internal home.
Okay.
And I guess that's where the closed bit comes from, because it's internal, right? It
sure.
So you get home to become an object in the same category.
I see.
Okay. So free monoids. Now let's pretend for a second that lists are actually free monoids. So you have a category of monoids on the left, which means objects are monoids. So you remember monoids, they have a combining operation and a neutral element. So that operation is associative, and there's an element that is neutral to with respect to this combining operation. and they are objects in this category. And morphisms in this category are monoid homomorphisms. That is functions that preserve the combining operation and the neutral element. And on the right we have set. So every monoid has a set that it is built from, right? The set or type of elements that you combine. But not every set is a monoid, right? So you don't see A in here. So that means that you can have a functor U, which is called the forgetful functor. Again, as with diagonal functors, many functors are called forgetful. This is one of them. So U forgets the monoidal structure, just gives you the set, and the free monoid is defined as the left adjoint to that forgetful functor. Yeah. So if you take an object a set A, its image under that left adjoint is gonna give you a free monoid on A, which for now we are pretending it is a list. Or any sequence type like seq or a vector, right? So its action on morphisms is a regular map, the Haskell map function, right? Now the interesting part. So C here is a fold map. You know fold map from the foldable type class. So there's fold map on lists. And the co-unit, so if you have a free monoid over something that is already a monoid, you can have you can apply the co-unit, which it happens to be a Haskell function called fold, which is also in the foldable type class. Here you can see that fold map G equals fold dot map G. You can also see that fold equals fold map of identity. So if we take G to be identity and A to be the same as M, this is gonna be so fold is gonna be fold map of identity. We have two different categories. This is where this adjunction diagram, being the same diagram, comes in handy, and Bartosz Milewski himself says that using so yeah, this is a weird heterogeneous pattern. So he notes that this involves two categories, but from the perspective that he's taking, this indeed looks weird because none of the other universal properties look like this, right? But here we are still using the same diagram. Yeah, and this is the definition from the book. But there's a problem. So lists are not free monoids, and the reason is that they don't, infinite lists don't, or infinite sequences don't really work consistently. Like for example, an infinite list would work differently compared to infinite vector, or no, infinite vectors don't exist even, right? And like compared to an infinite seek or a SNOC list, uh, and it's addressed in the article by Dan Doe. So I, well, not I. So he is defining this new data type by taking the signature of fold map and partially applying it to the collection. And this now is the actual free monoid.
I see. Yeah, I have one suggestion actually. Could you I know that you're planning on presenting this again. Would I think that you should have the links visible under instead of like rendered.
Like the actual URLs, right?
Yeah, I think the actual URLs would be good there.
Okay.
But that's very cool. I like that.
Yeah, so free monoids. Very similar concept to free monoids, although you might not think it is. So on the right, we have the category of endo functors. So this is, by the way, the notation for a functor category of functors with this domain and this codomain. Here they are the same, so these guys are all endo functors. They are objects of this category, and morphisms of this category are natural transformations. This is supposed to be the category of monads. Unfortunately, looks the same as monoids, right? But I don't know what's like the actual name in the diagrams for it. Yeah, so there is the monoidal structure. So you remember the definition for a monad. Needs to be an endo functor, needs to have a unit of a Sovereign signature and a multiplication. And you forget all of that monadic stuff and leaves you with just an endo functor. Now, free monad over a functor or over one a functor f, not sure about that, is given by the left adjoint, by the image of f under the left adjoint to that forgetful functor u. Yeah, so if you have a natural transformation from f, which you don't know anything about, like if it's a monad or not, to m that you do know is a monad, you can have a natural transformation from free f to m. So free monads are often used to construct EDSLs, right? So are you familiar with that? Like approaches for
anybody not
EDSLs?
anybody not familiar?
So in your functor f, you describe the operations of your language, right, as constructors. So it's a parameterized sum type usually, right? And in its constructors, you encode the operations of your language. And G is meant to interpret those operations into some target monad. And you're constructing a term of type free FA using a do syntax and binds, right, in monadic functions. And when it's time to execute it, you take your interpretation function, right, and apply fault free to it, and that is gonna run your program in M using these monadic operators. So yeah, these are all functions that you can find in control.monad.free. So the way so it's easy to see how free acts on objects, right? And on morphisms, you have this function hoist, either hoist or hoist free, for mapping natural transformations, for mapping morphisms in the endo-functor category to morphisms in the category of monads. And the call unit of this adjunction is retract.
So, question here. So you have two objects that have the same name on the left.
Right. Yeah. Sorry, that should be. Thank you. That should be free M. So like with free monoids, like this is a free monoid of something that's already a monoid. Yeah, this should be M. So a free monad over something that is already a monad. Yeah, that should be free M. Yeah, and retract just collapses all of the free layers. And this is the expression for unit. Also, do you know how free monads are defined? Right, it's something like fix of A cross f of itself. So free is A cross f of itself. I'm using this pseudocode notation. So do you notice how free is, how co-product is a left adjoint, and free is also a left adjoint, and free is defined as a co-product? I think that's kind of interesting. Okay, so now go free, go monads. So you have the category of endo-functors and the category of co-monads over C, and a forgetful functor. Now a different forgetful functor, right? Because different category. And co-free is the right adjoint to that forgetful functor, and co-free of F is the image of F under that functor. Yeah, so the idea with the intuition for co-monads is like it's some data structure or a table, something like that, with an element highlighted in it, right?
What makes it co-free?
What do you mean?
Well, so we kind of have like an idea of a co-monad, but co-free?
Yeah. For now, just think of it as like just a word, a part of notation.
Okay, got you.
I have no idea.
I see that it's dual to free, so that's cool.
Yeah.
Gotcha.
Yeah, it's just free is no, those. So use are different functors. That's not gonna work. I thought that would work like plus a is left adjoint to delta, which is a left adjoint to cross, right? But no,
But no,
there delta is the same, and here we have two different use.
I see. Okay.
Yeah, so if you have a W of A, you can apply section to it and get yeah, let's take a look at the definition actually. We have this weird. Okay.
Question?
Yeah.
Okay.
Is it right to say a free monad is a bit like taking some language generation rules and a set and exploding out all the possible words that could be in that language?
I think that would apply to call-free more. So this is collapsing.
Going the wrong direction.
So free monads are about collapsing rather than exploding. Right? And no, it's
Yeah.
a set of language, and free is a set of terms constructed using and using fault-free you collapse those using fault-free or retract those commands. Yeah, and I think this is more like exploding. So section is going to yeah, this is the definition, and yeah, two fields, a product with two fields. So this is going to be the result of extract, and this is probably the explosion you were talking about.
I'm very, very vague on everything. I sort of remember an adjunction, sorry, being described as having sort of like a forgetful direction and then the opposite free, air quotes, direction. And I seem to remember someone mentioning like a group and you forget that it's a group and then just take it to be a set. And then in the other direction, I had this picture in my head about, generating all the words of a grammar or something. But yeah. So.
I think this is what you're talking about, right? So you have a forgetful functor, and the left adjoint to it is the free functor. So the forgetful functor comes from the category of monads. So free gives you free monads, and if this was like GRP, right, the category of groups, the left adjoint would be a free group functor, and same for free monoids. Also, do you notice how free is a left adjoint and product is a left adjoint, and free is defined using co-product is a left adjoint, and free is defined using a co-product, and co-free is the right adjoint, and product is the right adjoint as well, and co-free is defined as a product. So that's interesting. Also, I'm not. We are coming to an end, and I am not mentioning a lot here. So initial objects, terminal objects, COM extensions, limits, co-limits, those are all adjunctions too. So to paraphrase Saunders-MacLean, all concepts are COM extensions, but a lot of concepts are adjunctions.
Awesome. So we'll have I don't know. Should we have any final questions before we stop recording here? All right. Jonathan.
Oh, I had one.
Yeah, go ahead.
It goes back a little bit. The idea of the internal HOM. So in certain cases, so I think Cartesian closed or whatever.
Yes.
The the set of all the arrows which you think is in set is also the same as the exponential object which is in the category itself, and which seems like that blew my mind when I figured out what someone was saying at that time. Sorry, just 1 second. Do you think we can swap those at the back?
Oh yeah, yeah. Just drive it in.
Sorry about that. And I was wondering if anyone thought like the idea of being closed, like is there any sort of like bigger concept that makes, that ties into this idea of this exponentials
Right.
kind of existing inside your category?
Right. So as you mentioned, if C is set, this is so home sets are objects in set, right? And they go inside or isomorphic to the exponential objects. Okay, one special case is if you know that your category is smaller than set or like a subset of set, you might actually use that to replace your functions with another object that acts like an exponential. That like that you're dealing with a limited set of types, and that is called defunctionalization. Yeah,
there's a categorical definition of defunctionalization that's very cool. Is there literature for that?
Yes, there's a talk by Milewski.
Oh, really? Oh, that's right.
I think
actually, I've seen that. I should have understood.
Functions with data.
Yes.
And also an article
right
in his blog.
Right. Oh, that's so cool.
But for an arbitrary category, yeah, that can also make sense for enriched categories. So there's a whole theory of its own called enriched category theory, and it has all of the parallel concepts, that is enriched categories, enriched functors, and enriched natural transformations, and I would guess enriched adjunctions are in there too. And so if C is the same category that is enriched too, this guy might also be an internal home. Like I don't know if such thing exists, a category enriched in itself. Yeah. But yeah, there is this case of defunctionalization, replacing the lambdas, which are function spaces, right? That are difficult to deal with a limited limited sets, right? That you know the size of.
This was awesome.
Okay. Back to the most important diagram.
I know. So this is the diagram that I think is. I definitely understand this to be why this is important here, and applying it. I think I agree that it's the most important one. Do you have a thought or a sales pitch for this diagram?
Yeah, because every other diagram is obtained from this one by plugging in things for C, D, and L and R, right?
Right. Awesome. All right. Anybody else have questions? Jonathan, Jason, Truba? Dope. Thank you so much, Oleg. This is really good. Let's give that a quick stop recording, and thanks again, Mike,